Then we have the high-level data link control. And this is currently being used, or is widely used, and it forms the basis for many other important data link control protocols that has been designed. Now, HDLC defines or has 3 types of stations. It has 2 types of link configuration, and it has 3 data transfer nodes of application. We are going to look at all these in the next slide. Now, it has 3 types of stations. These stations include the primary station, the secondary station, and the combined station. This is the combination of both 2 stations. So for the primary station, this controls operations of links, and frames that are being used here are called commands. And this maintains a separate logical link to each secondary station. But with the secondary station, this is under the control of the primary station. So the secondary station is under the control of the primary stations. And the kind of frames being used here are called responses. So take note, primary station deals with commands, secondary stations deals with responses. Then the third type of station is a combination of the 2. So here the combined station may issue commands and may issue responses. Then there are 2 links. The first is the unbalanced configuration, and this consists of 1 primary station and 1 or more secondary stations, and this supports the full duplex and a half duplex transmission. You remember we had 3 types of transmission: the simplest, full duplex, and the half duplex. Then the other link that has to do with the balanced configuration, and this consists of 2 combined stations. So the unbalanced one has 1 primary, then 1 or more secondary. Then the balanced configuration has strictly 2 combined stations. So we are looking at a combination of primary secondary and another combination of primary secondary. And it also supports the full duplex and the half duplex transmission. Now we have 3 types of data transfer. The first is the normal response mode, and here it makes use of the unbalanced configuration, and here also the primary station initiates the transfer to the secondary, and the secondary only gets to respond to the command from the primary. Multi-drop lines are used, the host computers are used as the primary, and the terminals are used as the secondary. Then we have the asynchronous balance node, and here it makes use of the balance configuration. Then either station may initiate transmission. I mean, either the primary or the secondary stations can initiate transmission without receiving permission. This is most widely used. No pooling overheads are also being used here. Then we have the asynchronous response mode. This one also uses the unbalanced configuration. Here the secondary may initiate transmission without permission from the primary, and the primary is responsible for the line, including initialization, error recovery, and logical disconnection. This is rarely being used anyway. Now let's look at the frame structure for HDLC. Now HDLC uses synchronous transmission, so all transmissions are in the form of frames. Now a single frame format is used for all data and control exchange. So below we have a diagram for the frame structure. At both ends is what we call the flag. It has 8 bits being used there. Next is the address, the control, the information, then the checksum, the frame checksum, which takes 16 to about 32 bits. Now the address can be extended, and the information or the data that we want to provide varies or is variable. You can vary the data in there, the size of data in there. So I've spoken about the flag field, and this flag field has a delimiter being represented by zeros and ones, we have a unique pattern of this nature. So you find this both at the beginning and at the end, and may close one frame and open another frame. The receiver hunts for these flags to actually tell the receiver that this is the beginning of the frame or this is the end of the frame. Now, a procedure known as bit stuffing is used to ensure frame level synchronization. What is this bit stuffing? Now, we have a frame to transmit, and know that the frame is made up of zeros and ones, and our flag is also made up of zeros and one. Now, a 0 is inserted after every sequence of 5 ones. Now, if the receiver detects 5 ones, it checks the next bit to see whether the next bit is a 0 or a 1. Now, we have an example. Above is the original pattern we want to transmit. Now, so the receiver or the transmitter looks at this bit. It counts 1, 2, 3, 4, 5. If it sees the first 5 bits as 1, then what it will do is that it will insert a 0. So you see that we have 1, 2, 3, 4, 5, and the next bit is 0. Then it continues 1, 2, 3, 4, 5. Then it will insert. So these are the bits that have been inserted. So we have a frame of the original, or we have the original pattern, and we have bit stuffed it with zeros. Now, once the data is being bit stuffed, then we put the flag. So you realize this is a flag that shows the beginning of the frame, and this is the end of the frame. It is after we have bit stuffed or checked for that consistency, that is when data is now transmitted on the line. So we have the inverted bit split, then we have the inverted bit merge, which merges 2 frames together. Then we have the address field, takes 8 bits, and all ones are served as, or are used as broadcast, which we learned this in networking. Then we have the control field. Here there are 3 types of frames that is being used for the control field. We have the information frame, the I, which is called the I frame. We have the S frame, which is the supervisory frame. Then we have the U frame, which is the unnumbered frames. Now the I frame carries data to be transmitted for the user. Then the S frame provides the ACK mechanism when piggybacking is not used. Then the U frame provides the supplementary link control functions. The first 1 or 2 bits of the control field identify the frame types. So we have the information field. Then we have the checksum sequence, which is the error detection code, the normal code, which is 16 bits. Then we have the optimal 32-bit CRC. Now, we want to look at the HDLC operations, and this consists of the exchange of I frames, S frames, and U frames between 2 stations. Now, there are 3 phases with regards to HDLC operations. First is initialization. Next is data transfer, then disconnect. So if I'm transmitting data between 2 stations, I first have to do initialization. So we have what's called a handshake, the 3-way handshake. I first send a message to the transmitter that I want to transmit something. It gives me a reply that I'm ready. Once that is established, I transmit the data. After the data is being transmitted, the next thing to do is to disconnect. Once that is done, that operation is carried out. The data is being transmitted from one end to the other. And this is what HDLC uses in its operation: initialization, data transfer, then after transfer of data, we disconnect. This brings us to the end of session 6. I'll see you in session 7.